Hey, it's Mr. Shrum, and welcome back to another physical science tutorial. And today we're going to look at the periodic table. We're going to use the table to identify information about an element and predict the element's properties. So we're going to show how this table is really useful in the realm of science and chemistry specifically. All right, so for the introduction. Scientists appreciate having rules and known answers to use in their day-to-day work, but puzzles are their real passion. They're trying to solve unknowns. They look for patterns in nature, then they use those patterns to predict the results of untried experiments or to consider unobserved phenomena. Scientists explore these patterns to make new discoveries, new inventions, and new theories. Sometimes this puzzle solving leads to a whole new understanding of nature. In the mid-1800s, scientists understood that different elements were actually composed of different types of atoms. They had also discovered the relative weights of those atoms, known as their atomic weights. But they still didn't know about the nucleus, electrons, protons, neutrons, or any other aspect of atomic structure. They had a two-part puzzle challenge to solve. One, why did different atoms act in such different ways? And two, how might these different behaviors help predict the properties of unknown elements and compounds? In the 1860s, the English chemist John A.R. Newlands noted some intriguing patterns in the elements. A series of short articles that appeared in the Chemical News from 1863 to 1866 tracks his developing thoughts. Newlands worked to put the elements in some sort of order based on the patterns he had observed. He began by arranging the elements according to their atomic weights. Then he related that order to previously identified similarities in their chemical properties. Newland's approach wasn't widely accepted at the time. During an 1866 presentation of his work, another scientist jokingly asked Newland whether he had ever examined the elements according to the order of their initial letters. That scientist dismissed Newland's discoveries, believing that any random arrangement of the elements would likely demonstrate occasional coincidences. Little did he know. So here's Newland's periodic table. It looks a bit different than Mendeleev's, or Dimitri's. It did have its shortcomings. He found numerical patterns in the known elements, but that was a problem in itself. Most scientists rightly assumed that some elements remained undiscovered. They understood that adding any new element between two known elements could destroy Newland's patterns. Critics also questioned the way he arranged certain elements. He grouped some of the heavier elements in odd ways to make them fit the pattern he noticed in the lighter elements. Well, despite these issues, Newlands was on the right track. A few years later, in 1869, the Russian chemist Dmitry Mendeleev used the same basic reasoning, and then he refined this approach into one of chemistry's most powerful tools, the periodic table as we know it today. So we're going to trace the work of these scientists and then see how they put it together and solve one of the scientific puzzles. Periodic table organization. So in order to get a clear picture of how scientists solved this periodic table puzzle, we're going to complete an activity using only the data available to scientists in the 1860s. So we're going to be handicapped in a way. Putting that data in order by atomic weight, as Newlands did, you'll look for groups of elements that seem to have similar properties. After you identify those groups, you'll try to spot patterns of similarity in their order. So in this activity, you will learn to organize the periodic table using the chemical database tool. So we're going to imagine that we're chemistry professors in 1860s. So over 160 years ago? Yeah. Like Newlands and Mendeleev, you're intrigued by repeated patterns of chemical behavior in the lighter known elements. And your job is to identify families of elements that behave similarly and then publish your results in this activity. We do have two advantages over Newlands and Mendeleev. Much of the data is already filled out in your table, including atomic ratios for the most common compounds of oxygen and chlorine. You have access to the internet and computer-based tools to fill in the rest. So I'll show you the tool. And then I'm gonna hide that. And then we're told what to do. In the tool, click on BE, which stands for beryllium. It's in the top left corner. And the compound list below the table is now filtered to include only those compounds containing beryllium. This list includes both formulas and common names of compounds. It may take some time to figure out how the alphabetization works with numbers and parentheses. First there is BE, then compounds with BE followed by a number of an item in parentheses. And then finally, beryllium followed by other letters such as beryllium bromine, and beryllium chlorine, dichlorine. Yes. So here we go. We'll click on beryllium. Bam. So click on BE beryllium and then scroll down. I'm going to see the chemical entities containing beryllium, the structure, the reactions forming, reactions using Wikipedia. Well, yeah. So we did that. Find BeCl2. So here we go. We found it. So we're typing in X to chlorine. So this is the ratio of this substance to chlorine. And we looked at beryllium and chlorine. See? And for every one beryllium, you have 2 chlorine. So that's 1:2 ratio. And that's why we put it there in that element to chlorine ratio. And then we're going to do the same for this element to oxygen ratio. So that's a 1:1. And if you need more information, you can look at the Wikipedia pages too. No, I don't want to do that. Beryllium chloride, and then you'll learn more about its structure and how it synthesizes and common reactions. And so you could write that here. So an inorganic compound with the formula BeCl2, colorless, hygroscopic. And if you're like, what's hygroscopy? That's the phenomenon of attracting and holding water molecules via absorption or adsorption from the surrounding environment. So you could go back. So we could say it's hygroscopic and dissolves well in many polar solvents. Hygroscopic or hygroscopic, however you want to say that. Okay, so you'll click on the element in the table, and then you'll look at the ratio of the element to chlorine, element to oxygen, other info, and then my family numbers. Some of these compounds may be tricky to track down. Common names will be mixed in with formulas in the alphabetical list. For silicone, silane will appear before silicones. So sometimes the names change, so don't let that throw you off. Finally, assign a family number to elements that seem to be closely related chemically. So if you're noticing, hey, these ratios are very similar, should they be in a family? Hey, these guys react briskly with water, or these three react briskly with water. Should those be in a family? I say yes. So here's the full numbered chart, and they didn't fill out the other info, but you can easily look that up. And then the family numbers. So you'll see that these match up with certain ones. See, like these three react briskly with water, so they're in family 2. And they have similar ratios of chlorine and oxygen. So then it says, how did you assign the family numbers? Were there certain patterns that jumped out at you? And so, for example, most of the elements reacted in very simple ratios with oxygen and chlorine. 1:1, 1:2, 2:1. There were more complex ratios through, though, for boron, carbon, and nitrogen. So look at boron. 1:3, 2:3, carbon, 1:4, 1:2. So those were a little different. Nitrogen, where was nitrogen? Yeah, here we go. So those acted a little more differently. The same ratio appeared for aluminum, silicon, and phosphorus. So they had 1:3s, 2:3s. There's aluminum and silicon. Once you assume those elements define 3 families, spaced 7 elements apart, you can see that the elements above and below them also have siblings 7 elements apart. So here we go. Here's 1, 2, 3, 4, 5, 6, 7, 1. See how that happened? And then 2, 1, 2, 3, 4, 5, 6, 7. So these 1s are 7 apart, these 2s are 7 spaces apart, and these 3s are 7 spaces apart. So you see that periodic jump, that periodic pattern. And that's what we mean by periods. In 1869, Dmitri Mendeleev and German chemist Rutherfords, we'll just call him Meyer for now, independently organized the elements into what would become the periodic table. Mendeleev published first, however, and he became, science famous. He organized the elements into rows and columns. Elements with similar properties fell into vertical columns, now called families or groups. So vertically, we call them families or groups, and the rows we call periods. And Mendeleev based his table mainly on atomic mass, but unlike Newland's, he sometimes broke the pattern to place elements in columns according to periodic property similarities. For example, although it left gaps in his groups 3 and 4, he placed arsenic under phosphorus because it had similar chemical properties. Mendeleev also placed iodine after tellurium, even though the atomic masses were out of sequence. He believed that the atomic masses of elements that did not fit in his pattern had been measured improperly. So here's how he predicted things. He left gaps in his periodic table that he believed represented elements yet to be discovered. Based on his table, he predicted the existence of at least 3 elements that were eventually discovered and which filled some of the gaps. In his process, Mendeleev predicted properties of element 72, which he called ecosilicon. Later, in 1886, an element that closely fit his description of ecosilicon was discovered in Germany and was named germanium. Its discovery showed the power of his periodic table to make chemical predictions. So this is what he predicted. This is what it actually was measured to be, germanium. Mendeleev tried to connect the periodic trends with atomic weight, but the discrepancies he noticed weren't caused by incorrect weight measurements. Today we know that an atom's weight has little direct effect on its chemical properties. Periodic trends among the elements are due to the structure of each atom, specifically the number of protons and electrons in each atom. In 1913, English chemist Henry Moseley found that he could determine the number of positive charges in a metal atom's nucleus by bombarding it with chemicals. Called an atomic number, this number is simply the number of protons in its nucleus. In a neutral atom, the atomic number also equals the number of electrons in the element. That's important because an element's chemical properties are tied to its electron structure. This last piece of the puzzle led to the modern periodic table in what is known as the periodic law, which is a periodic pattern appears in the physical and chemical properties of the elements when they are arranged in an order of increasing atomic number. So just to check your understanding, how is the modern periodic table arranged? We have, we know that chemical families or groups are in columns and periods are the rows. So instead of atomic weight, they are arranged by atomic number, and the chemical families or groups are in columns and periods are in rows. And we'll stop there before we talk about metals, nonmetals, and metalloids. And I will see you next time. All right, bye-bye.